Imagine you're standing on a bridge, maybe looking out over a river, feeling totally secure, right? Bridges are these huge symbols of connection, vital links. But have you ever really thought about what's going on inside them? The engineering battle against, well, everything. Weight, weather, corrosion. It's this hidden world of innovation, just focused on making sure these structures last. So today we're doing a deep dive into exactly that. How engineers are making bridges stronger, more resilient. We're going to get pretty specific, looking at the connections between materials like concrete and these advanced composites. We'll be focusing on something called shear connectors. And our guide for this is some really fascinating research. It's a computational study called Implementation of Interface Damage Model with Friction to Concrete-FRP Shear Connector by R. Vodichka and colleagues. Basically, they're using powerful computer models to simulate these tiny interactions that determine if a huge bridge holds up. So our mission for you, the listener, is to unpack how these complex computer models help us understand and improve these jigsaw puzzle type shear connectors. These ones made of concrete and fibre-reinforced polymer, or FRP, and we'll see how their shape and maybe surprisingly friction play this critical role in stopping failures. Let's get started. Okay, so that really sets the stage, but maybe we should back up slightly. Why fiber-reinforced polymers? Why FRP specifically for bridges when we've used steel and concrete for so long?
Yeah, good question. FRPs, fiber-reinforced polymers, they've really become a game changer in civil engineering, particularly for bridges. Think about what bridges go through: water, salt, temperature swings, heavy traffic, day in, day out. You need materials that can handle all that. FRPs are, first off, lightweight. That's a big plus, less load on the foundations. They also have amazing strength-to-weight ratios. Super strong, but not bulky. But maybe the biggest win for bridges: they resist corrosion. Steel, as you know, constantly battles rust. FRPs just don't have that problem.
Right. So it's not just about building shiny new bridges. It sounds like FRPs could be really important for, fixing up the ones we already have.
Oh, absolutely. That's a huge part of it. Their use is really taking off for rehabilitating, strengthening, retrofitting existing bridges. A lot of our older bridges, steel and concrete, they're showing their age. Corrosion, fatigue. FRPs offer a way to extend their life, boost their performance, often more cost-effectively than a full replacement. It's key for managing our aging infrastructure.
I can definitely see the appeal then. We know traditional composites like concrete steel, concrete timber.
Yeah.
So concrete FRP is really the next step, a significant advancement. But just having two great materials side by side doesn't guarantee they'll work together perfectly, right? There has to be a challenge somewhere.
You've nailed it. That's the core challenge. The overall performance of any composite structure, it really hinges on the connection between the parts. And that's where these shear connectors come in. They're absolutely critical. Their job is to transfer forces smoothly between, say, the concrete deck and an FRP beam below it. If those connectors fail, the whole system can be compromised. You could face serious structural problems. So yeah, optimizing these links is exactly what we're digging into.
Okay, but what happens when they don't hold? What does that failure actually look like down at that small scale? And how do engineers even start to predict or prevent it?
Well, when a composite structure starts to fail, cracks can show up in a couple of places. You might get cracks within the concrete itself, or maybe a fracture within the FRP. But often, the really critical failures happen right at the interface, that boundary layer where the two materials meet. To understand that, researchers use something called damage theory. It's basically a computational way to model how a material degrades. They often use what's called an internal variable to sort of track the damage state numerically.
So it's like a health meter for the material inside the simulation, predicting when it's starting to feel the strain. And the paper mentions an energy-based formulation. How does looking at the energy help understand failure in simpler terms?
That's a great way to put it, the health meter idea. The energy-based formulation, it's like meticulous bookkeeping for energy in the system. When you stress a structure, it stores energy like stretching a rubber band. When damage happens, like a crack forming, some stored energy gets released. New energy goes into creating that crack surface. Other energy might be lost as heat or sound. This formulation tracks all of that stored energy, the energy of new defects, dissipated energy. It helps predict how and when failure happens by looking at the energy cost of the damage.
Okay, that makes sense. And this interface, a super thin boundary layer, how do they actually represent that in the models?
In these models, they often treat it as an extremely thin adhesive layer, like a layer of glue, basically. When that layer degrades, they call it cohesive or adhesive contact failure. But here's where this specific research adds a really crucial piece: friction. A lot of older models either ignored friction or maybe only considered it right at the beginning when everything was perfectly bonded. This work, though, recognizes that even after the bond starts to fail, after debonding begins, the surfaces can still be touching, rubbing against each other. And that contact creates friction, which turns out to be really important.
Ah, okay, so it's not just about the initial stickiness, it's about what happens after things start to pull apart and how friction might step in. Interesting. So how do they actually design these better connections? You mentioned jigsaw puzzle connectors. What does that look like?
Well, traditionally you see a lot of rolled steel I-beams and bridges. But as engineers explore materials like GFRP, that's glass fiber reinforced polymer, for those lightweight, corrosion-resistant benefits we talked about, they needed new ways to make sure the forces transfer properly between the GFRP and the concrete deck.
And that's where these rib shear connectors come in. The jigsaw name is pretty descriptive.
It really is. These connectors are made by cutting regular shapes like notches or grooves into the vertical part of the web of the FRP beam. Then, when you pour the concrete deck around it, the concrete flows into these recesses. What you end up with are these vertically embedded FRP dowels and interstitial concrete dowels. Essentially, the concrete and the FRP physically lock together like jigsaw pieces. It creates a really strong interlocked connection for transferring those forces.
Okay, so the aim is to stop any slipping or separation. You mentioned 3 ways adhesive bonds can fail. Adhesive, cohesive of the adhesive, cohesive of the adherent. Why is knowing which type of failure happens so important for designing these jigsaw types?
Oh, it's absolutely critical for figuring out what went wrong and how to fix it. If it's adhesive failure, the bond breaks between the glue and one material. Maybe you need better surface prep or a different primer. If it's cohesive failure of the adhesive, the glue itself breaks, then the adhesive might not be strong enough, or maybe it wasn't applied right. So if it's cohesive failure of the adherent, the actual FRP or concrete breaks near the bond, then the issue might be the strength of the base materials themselves. For these jigsaw connectors, understanding the failure mode helps engineers fine-tune the shape and materials to make sure the weakest link isn't the connection itself. This paper is really focused on these interlocking types and how shape and friction affect how they resist these failures.
It sounds incredibly detailed. So modeling these tiny interfaces, especially with friction after debonding, how do they actually simulate something that complex? What's happening inside their computer model?
It's pretty sophisticated stuff. The researchers developed their own computational code in MATLAB. The basic idea is modeling that interface as an adhesion zone. Degradation leads to debonding, yes, but, and this is the key insight they build on, even after debonding, the surfaces can partially stay in contact. And this leftover contact is where friction comes into play, and it significantly changes how load gets transferred and how the structure behaves after that initial damage starts.
So it's not just calculating if it breaks, but simulating the whole energy management process, even post-crack. Can you break down those energy ingredients again, simply?
Sure. Think of it like an energy budget for the connector system. First, you have stored energy. That's the energy held in the materials as they stretch or compress, plus energy tied up in the interface's own deformation and damage. Second, energy from external forces. That includes the vertical pressure simulating the weight of the road deck above and the horizontal push or pull trying to slide the parts. And third, crucially for this study, dissipated energy. This is energy lost during damage, like when a crack forms and grows, and very importantly, energy lost due to friction as surfaces rub. They use a standard Coulomb friction model, which is a well-established way to calculate that resistance to sliding.
So a really complete picture of energy flow during failure. And they use advanced methods like the boundary element method, BEM, right? What's the advantage there?
Exactly. BEM is a powerful technique for these kinds of problems. It's efficient. Instead of calculating forces and stresses everywhere throughout the entire volume of concrete and FRP, BEM mainly focuses the calculations right along the boundaries between materials and, critically, along that interface itself.
Ah, so it concentrates the computing power where it matters most.
Precisely. It makes solving these complex, non-linear problems much more manageable and computationally feasible while still getting accurate results for the interface behavior.
Okay, that makes sense. Concentrate on the action at the boundary. So the bottom line is they're not just simulating breakage, they're simulating the whole process, including what happens after things start coming apart, especially that friction.
That's the key takeaway. Simulating the entire process, including the post-debonding phase with friction, gives a much more realistic picture of how these connectors will perform in the real world.
That is a remarkable level of detail. Okay, let's talk about how they use this model. You did a parametric study on a GFRP concrete connector. What were they trying to find out?
Right, they set up a specific simulation. They applied a horizontal displacement, essentially pulling the connector sideways while keeping a constant vertical pressure of 0.5 kPa on top, mimicking the weight of the deck. A parametric study just means they systematically changed certain design features to see how each change affected the connector's performance under that load.
And what were the key things they changed? The parameters.
They varied two main things. First, the shape of the connector's interlocking ribs, specifically a geometric value r, the radius of curvature of those ribs. They tested r from about 7 millimeters up to 20 millimeters, keeping the width stag constant at 50 millimeter. Second, and central to this paper, they varied the friction coefficient. They looked at a wide range from zero friction, 0, all the way up to a high value of me2. Though it's worth remembering that real-world tests usually find friction between these materials is more like 0.5 to 0.8.
Okay, so tweaking the curve of the jigsaw piece and how slippery the connection is, what did they actually find? What were the big takeaways about shape and friction?
The results were really illuminating. Initially, under low load, all the scenarios looked pretty similar on a force displacement graph. That's because everything was fully bonded. But as the load increased and debonding started, usually at one end, the interface began to slide. And that's where friction made a huge difference. It helped transfer the horizontal force, creating what they called a hardening effect. Basically, as it deformed, the friction kicked in, making it tougher to deform further.
So friction doesn't stop the first crack, but it dramatically changes what happens next.
Exactly. That's the fascinating part. Friction doesn't prevent the initial debonding, but it significantly helps the connector improve the load-bearing capacity. It lets the connector carry much more load even after the initial bond has started to fail. Think about this. With zero friction, the model showed the entire interface eventually debonding completely. But with friction, a good portion of the interface, especially in the area under compression, actually remained undamaged. That's a massive difference in behavior. Friction acts like a backup safety mechanism.
That really changes how you might think about designing these. How did friction affect the actual movement, the deformation, and the stresses?
Yeah, the model showed higher friction led to less overall deformation under the same load, so a stiffer, more stable connection. And friction completely changed how the stresses were distributed along the interface, particularly after debonding started. With friction, the tangential stress, the sideways stress, scaled up with the friction coefficient and followed that classic Coulomb rule once sliding began. Forces were shared differently and more effectively, helping prevent a sudden, total failure.
Wow. So did this complex simulation work actually lead to practical design advice? Any recommendations for engineers building bridges?
Absolutely. The study had clear takeaways for design. They found that a smaller radius of curvature results in a stiffer connector, even after some debonding has occurred. Combine that smaller R with higher friction, and you get a really positive effect on the overall structural stiffness. And here's something really cool. The simulation suggested an optimal R was around 9 millimeters for the best force transfer with moderate friction. And get this, that confirmed findings from previous experimental work where engineers had already landed on using an R of 8.5 millimeter.
No way. So the computer model essentially validated what engineers were already finding through physical testing.
Exactly. It's a fantastic example of computational modeling confirming and explaining experimental results. It builds confidence in both approaches.
Okay, so wrapping this up, what does this all mean for us, the people actually using these bridges?
Well, it means these incredibly detailed computer models are really powerful tools. They're not just academic exercises. They directly help engineers improve the design of absolutely critical parts of our bridges. By carefully considering things like the exact shape of a connector and this crucial role of friction, engineers can design composite structures that are more reliable, more durable, and ultimately safer. It's about building smarter right down to the microscopic level.
And it definitely highlights how valuable it is to combine these advanced simulations with hands-on experiments. Each approach informs and validates the other.
Precisely.
Yeah.
And the researchers aren't stopping here. They mentioned plans to look at how things might change with different material orientations like fiber directions and composites. It's an ongoing process of refinement.
Which brings us to a final thought for you, our listener. Just take a moment to think about it. Seemingly tiny details, like the exact curve of an interlocking groove, or the friction between two surfaces you can't even see. These things have huge implications for the safety and lifespan of these massive structures we rely on every day. It really makes you appreciate the incredible, often invisible, complexity and engineering skill that goes into making our world stand firm, letting us cross rivers and valleys without a second thought.